Okay, so I left off part 1 of this video by setting up part A of question 6, and then I went ahead and gave the answer for part B, but I'll go ahead and work it out here if you need it. So part B is probably the trickier of the two for this question, right? What is the rotation of the vertical axis that's 15 centimeters from one of the edges of the door? So this time I've got my door, right? But instead of doing it from the hinge or right in the middle, I'm doing it from some arbitrary point, right, 15 centimeters away from one of the edges. So that's what we're looking at here, right? So the way that we do that, if I ask you to find the moment of inertia about any kind of random point, if you will, the way that I hope we start thinking about this is we use the parallel axis theorem, right? If I want you to find the moment of inertia about some arbitrary point, we can relate it to the moment of inertia for the center of mass, and then plus m times the distance squared, where that distance represents how far is it from the center of mass. So we know for a door, if it's a solid door, if we're assuming it's a uniform door, which we will, the center of mass obviously would be right in the geometric center of this door. So it's right there, right? So we've got that to work with. We know then the door is 91 centimeters wide, so 0.91 meters. So then the center of that would be half of that, right? So 0.455 meters would be half of 91, 45.5 centimeters. And then how far would it be from this arbitrary point that I'm choosing to the center? Well, this point here is 15 centimeters from the edge of the door. So then it's just the difference between those two, right? 0.455 minus the 15. And so we get this distance d, which would be, if I again subtract those, right, just finding the difference there, be 0.305 meters from the center of the door. So that's going to be d for us. That's going to tell us how far away from that central axis are we. So then all we have to do from here is we just have to think about, right, you have to calculate what would our moment of inertia for the actual door be about that center of mass. And then I've got the mass of the door and I've got the distance from the center of mass, so it's not too bad. Right, so finding the moment of inertia, well, how would I calculate the moment of inertia for this rod-like object if I rotate it around the center of the mass? Well, the equation again for that, and this is something you would have accessible, but it would be 1/12 mass times the length squared. Right, so 1/12 mass times the length of the door, and then plus again the mass times this distance d that I just found. Right, so at this point, finding the moment of inertia, just plugging in the values that I know. So 1/12, the mass of the door, which they told me was 25. The total length of the door, which I know again is 0.91, it's 91 centimeters, so 0.91 meters. And then plus the mass of the door, so 25, times the distance to the center of the door from that arbitrary point that I'm choosing. So that's where that 0.305 comes into play, and then squaring that number as well. So my moment of inertia, right, for this point here, this point 15 centimeters away from the edge of the door, that's where I end up getting my 4.0508, and obviously you could round that off a little bit, but taking that to a few decimal places, that's where I got that moment of inertia from. So anyway, part B, like I said, of question 6 here, part B is probably the trickier part. It does take advantage of the parallel axis theorem, which is one that I would fully expect you guys to need to get comfortable with, so make sure you do start to think these over. And if you have questions with this type of problem, this type of question, just come find me so I can help give you some extra practice as need be. Okay, so question 7 is very similar to question 6. The first thing I am going to do here is I'm going to go ahead and make a note of some of my dimensions, right? So I know the radius is 6 centimeters, so 0.06 meters, and then the mass of the door is 21 grams, which would be 0.021 kilograms. So making a note of a few of those conversions before I even get started. But anyway, so we have a CD, and for those of you that don't know, right, the CD is the previous way of playing music before you had your MP3s, your iPods, and all those fun things. But anyway, right, I know you guys know what a CD is. I'm just making fun of you. But we're looking for the moment of inertia for rotation about the perpendicular axis through the center and through the edge of the disc. So let's start with the center, right? So if I've got my CD, relatively circular object here, I want to find its moment of inertia about the center, right, the central rotational axis there. So that one is one where I would just use, it's the center of mass, right? So I'm just going to use for a disc or for a thin cylinder, the moment of inertia for a cylinder or for a disc would be 1/2 m times r squared. Right, so that is my equation, and you should start getting comfortable kind of recognizing that as long as this is a uniform shape, which we'll assume it is, that it would just be 1/2 mr squared. So once I identify that, pretty easy question, right? I've got the total mass of the disk, which is 0.021, and I've got the radius of the disk, again, which I had to make sure I converted and found that radius, but 0.06, which I'm then squaring. Right, so the moment of inertia ends up obviously being a very small number in terms of our standard units. It ends up being about 3.78 times 10 to the negative fifth kilograms times meters squared. Right, so we do want to make sure we're getting comfortable putting that in the standard units, and it is okay obviously that it works out to be a very small measurement in terms of kilograms and meters squared. But anyway, I've got part A, and hopefully part A wasn't too tricky to then work through. So then for part B, what do we do? Well, part B, much like part B of question 6, is taking advantage of the parallel axis theorem. Right? So this time if I want to rotate it through an axis that's at the edge of the disk rather than through the center, well again, if I want to find the moment of inertia for any given point, then the moment of inertia is going to equal the moment of inertia through the center of mass plus this quantity of md squared, where d represents how far is it from the center of mass. Right? So the good news is we just found the moment of inertia for the center of mass, right? That is the geometric center of the disk, so that's what I found for part A. So I really already know this quantity right here is just 3.78 times 10 to the negative fifth. So if I want to find the new moment of inertia, again, it's just that quantity, 3.78 times 10 to the negative fifth, plus the mass of the disk, which again, 0.021 kilograms, times the distance squared, where again, that distance is how far away is it from the center of mass. Well, in this case, it's another radius right away, so it'd be the distance here, the d in this case would be 0.06 meters as well, right? Just like the radius, because that's how far it is from the center of that rotation. So just plugging that measurement in, squaring that measurement, and then calculating this whole thing. So obviously the first thing I hope you guys do notice conceptually, this should always be bigger, right? So the smallest moment of inertia is always going to be based around that center of mass. Anything that skews from the center of mass is going to have to be bigger because we have to be adding something to it. But anyway, that aside, right, at this point it's just a calculation game, and when we calculate that, we should end up getting something along the lines of 1.13 times 10 to the negative fourth kilograms times meters squared. Right, so anyway, question 7, much like question 6, taking advantage of our parallel axis theorem and hopefully helping us get more and more comfortable using that. Okay, so question 8 here is a lot like questions 6 and 7. And once again, we'll see that it takes advantage of the parallel axis theorem, at least for one part of this here. So this one's asking us to find the ratio of the moment of inertia through the second axis with respect to the first axis. So they're giving us a rod. They're giving us a thin rod here that has an axis of rotation straight through the center. So I've got my rod. I've got an axis of rotation, one of which is right through the center. And then I've got another one which they're saying is at the 30 centimeter mark. So on a 100 centimeter long rod here, the other axis of rotation would be somewhere about over here, right? So 30 centimeters away. So they're asking us to find the ratio between the two. So obviously that's an indication. We just need to find the moment of inertia about each of those and then set up a proportion between the two. So I'm going to start with using the moment of inertia just about that central axis, right? So I'm going to start by just finding what is the moment of inertia about that axis of rotation right in the middle. Well, again, for a uniform rod, we know that the moment of inertia about the central axis would be 1/12 the mass of the rod times the length squared. This actually works out pretty nicely because even though I don't know the mass, I'm just going to leave that as m. The length of the rod is just 1 meter, right? 100 centimeters, so just 1 meter. So this ends up just being 1/12 m times 1 squared, so obviously it just ends up being 1/12 m, right? So 1/12 m is my moment of inertia about the center axis there. So then I do the same thing for about this axis that is at the 30 centimeter mark, right? And just like we've seen for the last couple questions here, we know that to do that we're going to use our parallel axis theorem. So I'm going to find the moment of inertia about the point over here, and the way that I do that is I find my moment of inertia about the center, which I already know is 1/12, and then add to that, right, the mass times the distance away from the center of inertia there, and then squared, right? So d squared there is what I end up. Anyway, looking at this, we already know, again, this is 1/12 m, so we've already got that taken care of. This obviously would be plus m, and then how far away is it from the central axis? How far is it from the center of mass? Well, if it's at the 30 centimeter mark, that means it's 20 centimeters away from the axis of rotation, right? I'm going to go ahead and represent that in terms of L. And so in terms of the entire length of the rod, wouldn't that then be, if it's 20 centimeters, wouldn't that be the same as 1/5? And the only reason I'm going to do that, since it's 20 centimeters, it's the same as 1/5, that's going to make it a little bit easier to deal with these fractions here. All right, so I'm going to call that, instead of 20 centimeters, instead of 0.2 meters, I'm going to go ahead and call it 1/5. And again, I'm just doing that to help me out mathematically here. So then when I square 1/5, I end up getting my 1/12 m, obviously from the first part, plus 1/25 m when I square the 1/5 there. And so that's what I end up getting for my moment of inertia about this arbitrary axis here. So then when I do that, when I get a common denominator, right, for the two, of course the common denominator of this ends up being 37 over 300. I'm sure we were all comfortable with that, but obviously you guys could use decimals and that's fine too. But let's keep it exact if we can, so that's what I'm doing. But anyway, so that's then the moment of inertia about that point, right, about that arbitrary point, 30 centimeters away. So this is my second moment of inertia, if you will. My first one was just the 1/12 m. So then they asked me to find the ratio, excuse me, they asked me to find the ratio between the two. So the ratio between the two would be just I2 over I1, and then finding again from there. So 37 over 300 m divided by 1 over 12 m. Well, obviously the nice thing is the m's can cancel out. So I just have to simplify and clean up this fraction. And when I do that, I end up getting a ratio of 37 to 25. Right, so 37 to 25. The second moment of inertia has 37 parts. The first one has 25 parts. Obviously, you could simplify that a little bit more if you wanted to. I think that ends up being pretty close to 1.5, right? 1.49 or 1.5-ish. But anyway, it gives us the proportion, right? The ratio between the second moment of inertia and the first one, which ends up being about 1.5. So then last question here, again taking advantage of the parallel axis theorem. So a uniform solid sphere has a moment of inertia of I about an axis that's tangent to its surface. So I've got my sphere here, I've got the axis of rotation over here, and they've defined that as I. Well, I know that for any arbitrary axis it would really be I times the center of mass plus md squared, right? So that's what I'm looking at. So then all I have to really consider is, what would the moment of inertia about the middle of the sphere actually be? Well, for a sphere, the moment of inertia would be, it'd be 2/5 mr squared, right? If you look it up on the equation sheet, again, that's what you have to work with. And then over here, plus, this would be plus m, and then how far away is it? Well, isn't it a full radius away from the center of circle? So it'd be r squared, right? So I have 2/5 mr squared plus mr squared. And they've defined that for me as I. Right, so they're asking, what is the moment of inertia about the center? What is it in terms of I about the center? Right, so if I look at this, they've defined what they're calling I, they've defined as 2/5 mr squared plus 1 mr squared. Well, wouldn't this be the same thing as 2/5 mr squared plus 5/5 mr squared? Right, doesn't that end up being the exact same thing? Right, so the reason I'm considering this is, what does the total end up being? Well, they've actually defined I as what would be 7/5 mr squared, right? Mathematically, I'm just adding those two up. So they've defined this arbitrary measurement of I as what we would call 7/5 mr squared. So then how much of that does the moment of inertia about the center actually account for? Well, the moment of inertia about the center only accounts for 2/5 of the 7/5, right? So isn't it only counting for 2 of the 7 parts, 2 of the 7ths? And so that's where our correct answer for this is going to be, it's 2/7 of our I, right? This is accounting for 2/5, this is accounting for 5/5, and we know the total I is representative of 7/5 mr squared. So like I said, I know question 9 here, probably a pretty tough multiple choice question. If you do have any trouble with kind of the reasoning behind this, obviously feel free to let me know, but that does finish out then this second part of homework 7-2.